doing that, because it is, in a way, rather simple-minded. I'm not going to do all the proving of stuff now. Here is the confidence interval, and that's it, basically. Let's look at the formula. It takes the proportion and subtracts something and adds the same thing. And that is kind of a maximal error thing, like we do for a mean a few weeks ago. So the observed thing plus minus the maximal error with some confidence, right? That's the same idea. We also use, as you can see, the normal distribution, the standard normal, that is table 3, or table 3, or the Q-norm function of R. So we use the standard normal. Hey, how can that be? Will we use the standard normal in this case? I said that the situation is like flipping a coin, right? It's like in a lot of times counting how many successes or failures. That's the binomial. So basically, the underlying theoretical model for what's going on, probability model for the system, would be a binomial. Can you recognize, remember what is the variance of a binomial? Say if x is binomially distributed with p and n. Well, the variance was np times n minus p. I showed you this many weeks ago in the beginning of the course. So look at this. This term here is actually, this means that the variance of a p hat in a binomial, that is then 1 over n squared times the variance of x, right? Because the x, the p hat is x divided by n, so I take the n squared out, meaning that if I do like this, the variance here becomes p times 1 minus p divided by n, because n squared takes the 1 of the n here. Let me do like this to distinguish the two expressions. So, look at this, p times np, p times 1 minus p over n divided by n, and this is exactly this term here, the square root of this. Instead of p, which I don't know, I have plugged in the observed proportion, right? Here, that's p hat, p hat. So I plug in the proportion, and I get the standard deviation from the binomial. Remember, I also showed you weeks ago when we did the discrete distributions that you could, at least if n is big enough, you can approximate binomial probabilities by normal probabilities. And that is the theoretical result which is underlying this confidence interval. So we use normal probabilities to put up a confidence interval. At least this one works if both n and np is at least 15. That was the rule for the de Moivre-Laplace formula, which was the approximating formula for binomial and the normal distribution. A confidence interval. Now I brought in a couple of prepared examples. Let's just do that. How many of you in here are left-handed? Raise your strong left hand high in the air if you want to play the game. Can you raise it high so I can see it? Let's count. How many? 1, 2, 3, 4, 5. Only 5 strong left hands in here. So if it was left-handed, I would have x equals 5. How many? How large is the sample? 10, 20, 30, 40, 50, 60. 50. Out of 50 people in here, 5 of you were left-handed. So if I were to estimate the proportion of left-handed people in Denmark, I would estimate it at, of course, x over n, that is 10%, right? I would estimate the proportion of left-handed in Denmark at 10%. The female engineering students, how many are in here? Can you help me? Just, it's not that just 6, 7, 8, 9, 10, 13, 14, 15, 16, 18, 21, 24, 5, 25. That's a good number. I would estimate. It's a nice estimate, but probably still a bit wrong. Yeah, that could be all. That's a good point. There could be something wrong with my sample here. It's not a random sample, right? It's a convenience sample, as some would call it. There is even a name for those samples which are meaningless. This name is called a convenience sample. It is taken at convenience because you are here. And maybe there are a lot of selections. Maybe guys have, as I should be careful about, it was suggested that maybe males have more difficulties in actually showing up here at 8 a.m. in the morning. There could be all sorts of possible explanations for this. Maybe I was probably cheating a little bit on the n. Probably the n is a bit above 50 here, but I chose it to have a nice computation here. Proportion in favor of Obama, actually. We are having a bit of challenge here for some of these, actually. Let's say it was 40, taking your own poll from last week, so proportion of you. I mean, you're not going to vote. Obama would love it if that was the case. We had, let me see, 47 out of 49 were actually in favor of Obama. That's almost 96%, right? That's a pretty nice poll for the Obama. But then again, we are not going to elect the next US president. I'm sure the Americans are happy with that. Those damn communists in Scandinavia is not going to... No, okay. I should be careful here. Things are being recorded. Actually, for some of these examples here, I'd like maybe to take... We do have a problem with some of these to apply our formula, because we should have both x and n minus x should be larger than 15 for the formula to be valid. And here we have n minus x up here. It's actually only 2 in the Obama case. So actually the formula would be questionable and even maybe not valid. We cannot use the formula here. That's just as a... Let's do the proportion of teachers unhappy with students then. Let's do this one. Because that was actually 26 teachers out of 51 teachers, if we take the definition by the newspaper, taking both the thing with the sometimes, the often, and almost always. Then 26 teachers out of 51 teachers thought there was a problem, right? So the proportion of teachers finding there is a problem is 26 over 51. Should we do some computations? Let's do them in our favorite tool here. Now I had 26 out of 51, right? 26 out of 51. What is p hat? What is the p hat? 51%. 51% thought there was a problem. What is the uncertainty? What is the confidence interval for this one? Well, please remember that my formula on the slide said that I should take plus minus. Actually, I should take this one. Plus minus if I take the 95% confidence interval, I take the standard normal quantile point, which you should remember. The 2.5% point, that's the 1.96. Set alpha half with an alpha of 5%. I take square root of p hat times 1 minus p hat over n, and I see what is this number. This number becomes 0.14. 0.14. So the confidence interval. The confidence interval is 95%. I take this example here, finding the confidence interval for these numbers. 95% confidence interval. Really good order here, like this. Would be 0.51 plus minus 14%. That is somewhere in between, what is this? 37% and 65%. This amount of teachers, between 1/3 and 2/3 of teachers, would find it a problem if you define a problem being that sometimes people are not prepared, right? Now this at least sort of gives us a bit more sort of feeling of maybe it's 50%, maybe it's only 1/3, maybe it's 2/3. I mean, it could be even worse also. I mean, we don't know. And then again, as I said last time, one thing is what teachers think. And who, maybe also, what about the sampling here? This was some newspaper calling around maybe to university teachers, emailing maybe university teachers. I get a lot of those emails and get a lot of those phone calls. And I'm the most rude guy you can ever call on the phone. I'm trying to get like be blacklisted on these lists not to be called again. And I can see it works. My wife gets called again and again. She's too nice to lay them off. I just say, I don't want to speak with you. I don't know, it's young guys like you sitting out there. I try to be friendly, but I simply don't want to spend my time. Anyway, please do. Maybe the people answering such a questionnaire or reacting are those that are really, those few that really think it's a problem. I mean, I don't think it's a problem. I don't care. I don't want to answer this one, right? So we may have a selection bias again in the sampling. We should always be worried about that. So there is a high uncertainty, and of course we should be worried about the sampling. The sampling is the basic setting. We can always discuss that if you go behind the numbers. The statistical uncertainty is something we can calculate, we can find out. That was not quite. Just a comment. I mean, I don't give you this. I gave you a formula, if I go back, for finding the confidence interval. And then I told you, you cannot use it always. I was a bit too fast here in my point here. Actually, the correct thing is to say that n times p and n times 1 minus p, actually. The other thing doesn't really make sense if you think about it, to say that. Both of these two should be larger than 15, not the n itself, actually. That was not, I mean, it doesn't make sense. I mean, if NP is larger than 15, then N is also. So that was kind of an empty thing to say. What I meant was that NP and N1 minus P, that is, we couldn't have too few or too many. It's like, if you have 47, it should not be 0, 1, 2, and it should not be 45, 46, 47 times responses. So that is the correct conditions for the confidence interval. Thanks. I'll try to do something on the video there. That's a challenge to us, but we'll see how we can do it. At least if the data comes out, I mean in the one, it's when the data comes out extreme, either in the one or the other extreme, or n is very small, we have a problem, we cannot use the formula. Well, dann haben wir andere Methoden, ja? There are other ways here. It's also in the book. You can find confidence intervals based on the binomial distribution. It's a bit more technical, and you have to keep your tongue a little more straight in your mouth to actually do it. It's described in the book chapter, actually. I'm not going to go into it. It can be done. It's just to say. It's not like everything falls apart. You can do it. It's just more tedious. That was the second part. So, we move on.